In this video, I want to show you how to exploit the, the properties of the natural log and the easiness of taking derivatives of stuff inside of natural log. We have this thing called logarithmic differentiation. Here we go. Here's an example of how it works. Suppose I've got a function. Now I'm going to start with a function that I do know how to take the derivative of anyway, but I'm going to do it a different way and see how it might be actually easier to do this. So let's take something like 2x minus 7 squared times x minus 4 cubed, all divided by 4x squared plus 1 to the 5th power. Okay. Now, this is a quotient, so I could use the quotient rule, and within the quotient rule I've got to take the derivative of the top, and the top is a product, so there's a product rule that I might use, and each of the things in a product is a power, and you know, I could do this with the rules that I already had. However, what I want to do is I want to do what I call logarithmic differentiation, because with this being a quotient of powers of things, take the natural log of both sides. So I've got the natural log of y equals the natural log of all this stuff, 2x minus 7 squared, x minus 4 cubed divided by 4x squared plus 1 to the 5th. Okay. Now, I'm going to use the properties of logs to break this thing up, because this is the log of a quotient. Well, the log of a quotient is the difference of the logs. So what I have here is log y is equal to the natural log of 2x minus 7 squared times x minus 4 cubed. So there's the numerator, and then minus the log of the denominator. Then I'm going to use another property of logs and break this up. So I have natural log of y equals the natural log of this first thing, 2x minus 7 squared plus natural log of x minus 4 cubed minus the natural log of, so this should be in parentheses, this should be in parentheses, 4x squared plus 1 to the 5th power. Okay. Now I'm going to use one more property of the logs to break this up even further. And this may seem like a lot of work, but actually it's work that I'm doing far more steps than I really need to write down. And I'll show you how I would normally do it in a moment. But the log of something to a power, the power can be out in front as a multiplier. So natural log of 2x minus 7 plus 3 times the natural log of x minus 4 minus 5 times the natural log of 4x squared plus 1. Okay. Now, I have broken this down into as small as I'm going to make it, and let me point out that for myself, I would probably not write down these steps here, here, and here as I go right to this one. Because I'm taking the natural log of both sides. That's the natural log of y. And I know that what's going to happen on this side is that logs of quotients turn into differences, and logs of products turn into sums, and exponents get written out in front. So notice this 2 is that 2 right there, and this 3 is this 3 right here, and this 5 is that 5 right there. And anything that's in the numerator, any of these factors here that's in the numerator, ends up with a plus sign in front of it. And in the denominator, you end up with a minus sign because you're subtracting. So after you do a couple of these, you see the pattern, and you can just say, well, I'm just going to go straight from here to here. So it really isn't much work to get to here. Now, the whole point of doing this, because I haven't done any calculus yet, I haven't taken any derivatives, I'm going to do that now. I'm going to say, okay, now I'm going to implicitly differentiate with respect to x. And it's implicitly now because I don't have just y equals, I've got some function of y. So I'm going to take the derivative of the natural log of y with respect to x and take the derivative of all this stuff with respect to x. And again, I'm writing down more steps than I would normally do just to show you every step, but so with respect to x of all this stuff, 2 natural log 2x minus 7 plus 3 natural log of x minus 4 minus 5 natural log of 4x squared plus 1. Okay. Now, Derivative of the left-hand side. Derivative of the natural log of y with respect to y would be 1 over y. But I'm not doing it with respect to y, I'm doing it with respect to x. So multiply by dy dx. Okay. That's equal to, and now I got to do this derivative. But the beauty of the natural log is that it turned quotients into differences, and I would much rather take the derivative of a difference than a derivative of a quotient. And likewise, it turned products into sums, and I would really much rather take the derivative of a sum than a product. And it took these powers, which you'd have to use a power rule to take a derivative, and wrote the power out in front as a multiplier. And man, to take the derivative of just a function times a constant, well, that's easy. So here we go. Take the derivative of this first part. The 2 just comes along for the ride. And the derivative of the log of 2x minus 7 is going to be 1 over 2x minus 7, right? Whatever's in there gets put on the bottom. But then the chain rule says multiply by the derivative of what's inside. The 3 comes along for the ride. The x minus 4 goes in the bottom. The derivative of the x minus 4 gets multiplied on the top. The minus 5 comes along for the ride. The 4x squared plus 1 goes in the bottom. The derivative of the 4x squared goes on the top. Then I can solve for dy dx. Multiply both sides by y. And what do I have? I've got 4 times 2x minus 7, so 4 divided by 2x minus 7 plus 3 divided by x minus 4 minus, what is that, 40x over 4x squared plus 1. Now I'm not done yet because the problem wasn't implicit. The problem was explicit. I gave you y equals this function of x. I want the derivative in terms of x. So the one thing I now have to do is I've got to replace that y with whatever it is. Well, what is y? Y is the function you started with, right? So I've got 2x squared minus 7 squared times x minus 4 cubed over, what did I have? 4x squared plus 1 to the 5th power. That's the y. And then times all this stuff here. 4 over 2x minus 7 plus 3 over x minus 4 minus 40x over 4x squared plus 1. And there you have the derivative. Now, yeah, it seems like that's a lot of steps. But again, I think that when you get practiced at this, you can anticipate what's going to happen with this log. You can anticipate this line here. Then you take the derivative, and probably the next line I would write down is this one right here. In fact, sometimes I even not do that because I know that this is going to be 1 over y, and the y would come up here. As you're doing these, practicing these, the homework out of the book or online, wherever you get it, I would write down more steps to start with, and as you start feeling comfortable, see if you can do it in fewer steps. With logarithmic differentiation, you're taking the log of both sides. This side's always a log y, and the derivative always looks the same, 1 over y times dy dx. And then you multiply both sides by y. So every time you do this, you're going to have that y that sits up front here, the original function, times all this other stuff that you got by taking the log of the right-hand side and breaking it apart and taking the derivative. Okay. So we do a little algebra first, and then we implicitly differentiate, and then we solve for dy dx. That's logarithmic differentiation.